AI has continued to exceed the public's expectation of its seeming ability to think and complete tasks in ways previously thought only by humans. It's already woven into applications in our everyday lives, such as search engines, language translators, spell checkers, and generative imaging. Within an AI program, many optimized parameters form a network that selects an output for a given input. The more parameters, the more powerful the AI. For example, ChatGPT-4 has an estimated 100 trillion parameters. With so many parameters, AI requires extensive computing power and memory. The computer hardware that performs all those calculations is based on semiconductor microchips, manufactured using predominantly silicon. Computing power of a microchip often depends on how much we can shrink these semiconductor transistors while maintaining high quality manufacturing. Shrinking them allows engineers to pack more and more transistors onto a single chip, simultaneously reducing waste heat, meaning reducing electrical consumption per transistor, and improving the chip's computing power. Throughout semiconductor manufacturing history, manufacturers have progressively shrunk the transistors, packing more and more transistors onto a single chip. This trend was famously described by Moore's law, where the number of transistors on a microchip roughly doubles every 2 years. Current transistors have typical width of 10 to 20 billionths of a meter, less than 100 silicon atoms wide. These transistors and other components are integrated into a single circuit fabricated on a high-quality silicon wafer. Given the demand for AI programs, there is a substantial drive to improve the performance. Semiconductor manufacturers aim to shrink the transistors further to only 5 billionths of a meter each. However, there is a fundamental limit to how much we can shrink the transistors. Therefore, other approaches, such as stacking the transistors vertically, leading to 3D circuits, are used to improve performance. Alongside this, microchips optimized for AI have now started to appear in laptops and computer hardware for ordinary consumers. These have thousands of cores that perform the calculations in parallel for greater efficiency. This allows smaller AI programs to be run using local computing hardware, eliminating the need to communicate back and forth with a data center. Although they are less powerful than the larger AI models, they can be more responsive to new requests and raise fewer concerns about data privacy. Therefore, progress in semiconductor technology is enabling more accessible and powerful AI, which will benefit ordinary consumers through AI-enabled software with better performance than standard software.